Hi, everyone. I'm Haoyu from the Cognitive Computation Group at the University of Pennsylvania. In this presentation, I will present our paper, Extracting or Guessing, Improving Faithfulness of Events Temporal Relation Extraction. This is a joint work with Hongming Zhang, Yuqian Deng, Jacob Gardner, Deng Roth, and Muhao Chen. Event temporal relation extraction is an essential step towards understanding narrative texts, such as stories, novels, news, and guideline articles. With a robust temporal relation extractor, one can easily construct a timeline from text and capture the trend of temporally connected event mentions. Most existing temporal relation extraction models are developed with the data-driven machine learning approaches, for which recent studies also incorporate advanced learning and inference techniques. Though these recent approaches have achieved promising evaluation results on benchmarks, whether they provide faithful extraction is an underexplored problem. The faithfulness of a relation extraction test system is not simply about how much accuracy a system can offer. Instead, a faithful extractor should concern the validity and reliability of its extraction process. Specifically, when there is a temporal relation to extract, a faithful extractor should generally obtain what is described in the context, but not give trivial guesses from surface names or most frequent labels. Besides, when there is no relation described in the context, the system should selectively abstain from prediction. So we observed that in recent models, biases from prior knowledge in pre-trained language models and statistically skewed training data often lead to unfaithful extractions. To address these two kind of faithfulness issues in temporal relation extraction models, in the training phase, we add tense information of verbal events into the context of events and obtain event representations from neural encoders. And then we use multi-layer perceptron to get the model prediction of categorical distribution for temporal relations. To improve the selective prediction ability of the model, we parameterize a prior distribution over the categorical distributions such that the model can predict properly over both in-distribution and out-of-distribution data. In the inference phase, we propose to conduct counterfactual analysis to attenuate the effects of two significant types of training biases, the event trigger bias and the frequent label bias. After that, we leverage temperature scaling to obtain recalibrated and debiased categorical distribution over the temporal labels. To add the tense information into event context, we leverage an off-the-shelf tense tagger developed by Zhang and Blake. Specifically, we enclose the first and second event with @ and pound symbol respectively, and prepend their tense information to their spans with asterisks and carets. This is inspired by Zhou and Chen's 2021 work on improving entity representation by prepending entity type information into the mentioned spans. Observing the reliability diagrams of existing temporal relation extractors, we observe that these neural models tend to be overconfident in their prediction and thus cannot abstain from prediction appropriately. To address this, we model the vague relations in the temporal relation datasets as out-of-distribution cases, which are different from in-distribution data describing other temporal relations like before, after, and simultaneous. The goal of providing high-quality confidence estimates requires the model to yield a sharp predicted distribution centered on one of the labels when it is confident, and yield a flat distribution over all labels for out-of-distribution inputs. To achieve this goal, we explicitly parameterize a prior distribution over our model categorical distributions. Because of the tractable analytic properties of Dirichlet distribution, we choose to parameterize a sharp and a flat Dirichlet prior over the model predicted categorical distribution for ID and OOD inputs respectively. After the parameterization process, the gap between our model's accuracy and expected accuracy becomes smaller, thus reflecting a more proper estimation of model uncertainty. Given that we have observed two types of biases in existing models, namely the event trigger bias and the frequent label bias, we ask the following questions. What will the model prediction be if seeing the whole context? What will the model prediction be if only seeing the event triggers? And will the model predict anything even if it sees nothing? Inasmuch as we have described the learning process of the model, we know how to obtain model prediction given full context and can easily answer the first question. The second and third question, however, are hypothetical questions whose answers reflect the confounding biases that we would like to mitigate. With attention masks in recent pre-trained language models, our model can be endowed with imagination ability effortlessly. By inputting a counterfactual instance with the context masked, while maintaining the spans of event triggers to the model, we can obtain the model prediction given event trigger names only. And by setting an empty instance, we obtain the model prediction where no contextual information is given. Intuitively, these two predictions thereof provide measurements for the trigger bias and label bias. Nevertheless, the debiased model is not perfect. A minor drawback lies in that its confidence estimates might have been shifted by element-wise subtraction through this equation, and it provides prediction. Even though it provides predictions with good evaluation results, its confidence estimates is not good at all. Therefore, we employ temperature scaling as our last step to allow for recalibrated confidence measures for the model. During inference, we use the entropy of the final categorical distribution, which captures the uncertainty encapsulated in the entire distribution. On the development set of vague examples, we find the optimal threshold below which the model predictions are considered equivoques and the inputs are OOD. We evaluate using the following three datasets: mattress, mattress DS, and TDD scores. Mattress mainly measures how well the model predicts for short distance event pairs, whereas TDD scores measure how well the model predicts for long distance event pairs. The mattress DS is a dataset that we created for evaluation of our models when dealing with data with distribution shifts. We replace frequent triggers in the mattress step and test sets that appear within the top 5,000 frequent lemmas with their uncommon synonyms, and replace infrequent triggers with their frequent synonyms from the list of frequent lemmas. Mattress DS also presents a mismatch between the training and test distributions or dataset shift, where distributional uncertainty often arises. In the table below, we show the evaluation results on these datasets. On mattress, the SADA model still offers the best performance in terms of micro F1, whereas our model achieves comparable macro F1 and lower calibration error. In contrast, our model's proposed faithful temporal relation extractor outperforms baseline models in terms of all evaluation metrics under dataset shifts caused by the replacement of event triggers in mattress DS and also the long context distance between global event pairs in TDD scores. Specifically, our model shows a significant gain of 2% macro F1 and 0.8% micro F1 over the solid model on mattress DS, and surpasses the previous solid model on TDD scores by 1% micro F1, not to mention the improvements on confidence calibration. We also apply our model to the timeline construction task, where the goal is to sort a list of events in a document in chronological order. To construct the timeline, our model first constructs a directed graph, G, with a predicted non-vague temporal relation between every event pair. Then the edges in G with lowest confidence scores are removed until G becomes a directed acyclic graph. Finally, the timeline is generated as the linear ordering of vertices in the DAG by topological sorting. In this way, we circumvent the possible conflicts in model predictions for timeline construction, and the faithful removal of least confidence edges serves as an examination on the quality of model predicted confidence. On three datasets, we report the accuracy of exact match and average minimum edit distance between predicted and ground truth timeline as our evaluation metrics. From the table on the left, we can see that our model outperforms both baselines on timeline construction by a large margin in terms of both metrics. Specifically, under dataset shifts within mattress DS and TDD scores, our model surpasses the best baseline by 11.4% and 14.4% in accuracy, while drastically reducing the minimum edit distance by relatively 11.4% and 28.9%. We also provide a case study on timeline construction for three events. The reason why our model predicts after for the third pair is probably due to the misleading temporal cues in the text Thursday and Tuesday, while the long distance between events undermines the confidence for this prediction. When our model builds a directed graph with three relations, a cycle is identified, and then the edge with the lowest confidence is removed from the graph, and thus our model constructed correct timeline. Without tense information, the model would tend to make wrong prediction concerning the second event whose trigger is an adjective. And without Dirichlet prior or temperature scaling, the model calibration becomes noticeably worse. In conclusion, we investigated on improving the faithfulness of event temporal relation extraction from two perspectives. To enhance the selectiveness of model predictions, we parameterize Dirichlet prior over the model predicted categorical distribution to regularize the model to behave differently with ID and OODD data. To mitigate two types of biases from pre-trained language models and training data, we add the tense information of the events to obtain robust event representations, and also conduct a counterfactual analysis to reduce the risk of carrying prediction shortcuts into the inference stage. We also employ temperature scaling to combine the two faithful perspectives, which recalibrates the confidence measure of the model after bias mitigation. We created a new variant of the matrix dataset called matrix DS, which serves as an examination of the model under OOD data with dataset shifts. Through experimental analysis on matrix DS, and TDD scores, we demonstrate that our model faithfully extracts event temporal relations and timelines from text, so as to generalize well under distribution shifts. Thank you for listening.